So in this exercise, you will see the questions related to topic waves. In the question, a ripple tank is used. What is the main purpose of a ripple tank? It's used to observe or demonstrate the properties of the wave, like reflection, refraction, diffraction. And why we use a ripple tank? Because it's easy to produce these waves and observe them. That's why we are using this ripple tank. So a ripple tank is used to demonstrate the interference of a water wave. The two dippers D1 and D2 produce a coherent wave. What is the meaning of the term coherent? Means that they have a constant phase relation and we're having a constant frequencies. And they have illustrated in the figure 5.1. The lines in the diagram represent the crest. These are actually the wave front. What are the wave front? When we have so many waves which are moving in one direction, so instead of drawing all of them, what we can do, we can use the wave front. And different types of wave, like if I join all the crests, that line is known as a wave front. So if the wave is traveling in one direction, we use a plane wave front. If wave is spreading like in different directions, then we use a curved wave fronts. We just make a curvature which shows that the wave fronts are traveling in different waves are traveling in different direction. And if it's a circular wave front, it means that it's traveling in all the directions. So the line on the diagram represent the crest. The waves have a wavelength of a 6 centimeter. One condition that is required for an observable interference pattern is the wave must be coherent. Describe how the apparatus is arranged to ensure that the waves from the dippers are coherent. So what should be the condition that the waves which are produced here are coherent? How these normally dippers are working as they're how it is producing a ripple. If this is a side view of a ripple tank, like you are looking from the side, and here we have a water. And this is a dipper is there inside a water. So we want them to vibrate in the same manner. How it works, like usually these dippers are connected to an AC supply, alternating current supply. The frequency of the supply matches with the frequency of the dipper and it causes vibration. Like the dippers will vibrate to and fro, move up and down, and as it disturbs the water surface, it start to produce the ripples, waves. So we want to make sure that they vibrate in the same manner. So if we want them to vibrate in the same manner, then what we should do, we should connect them to a same supply. So dipper should be connected to a same supply or same motor or same vibrating object or vibrator, you can say. So they will vibrate in the same manner. Is it clear, the first part? How the apparatus is arranged to ensure that the waves from a dippers are coherent? Next is state one other condition that must be satisfied by the wave in order for an interference pattern to be observable. If we want to observe the interference pattern, first thing is the waves should be coherent. The second, they should have a comparable amplitude. Like I cannot observe the interference. Interference means combination of the wave. I cannot observe the interference of these two waves. One is like example a 10 centimeter and another one is like example 1 centimeter, even though they have the same frequencies. But this is not a considerable amplitude. So they should have a considerable amplitude, like similar amplitude, you can say, for to observe the interference. Because even though this added, let's say this was having a height amplitude of 10 centimeter, and this was having an amplitude of 0.05 centimeter or 0.005 centimeter. So when I observe the amplitude, the change in amplitude will not be considerable. So that's why to observe the interference pattern, the wave must be coherent and their amplitude should be comparable, or you can say similar. Similar is a right term rather than comparable. So you can use the term they should have a similar amplitude. The light from a lamp above the ripple shines through the water on a screen below. Describe one way of seeing this illuminated pattern. How we can observe this illuminated pattern? So we can use a stroboscope as well as we can also use a camera. I will show how it looks like the pattern when we are observing the interference pattern, how the ripple tanks looks like. So this is how the ripple tanks look like. Like we have a tray which is filled with the water. We have the vibrating object. In this case, we are using a single vibrating object, but we can also use separate, like here, one large object is connected to the vibrator, but what we can use, we can also use small dippers as well. This is how the ripple tank, and there is a lamp on the top when light is passing. So when the light passes, we see the pattern on the screen here below. Below the table, we see observe the pattern of the wave. Actually, we don't see the wave, we'll observe the wave fronts. This is the actual, these are the dippers. You can see here, these are the dippers which are vibrating and producing a pattern of the wave. And these two waves will interfere. When these two waves will interfere, we'll observe either a constructive or destructive, but it should be highly coherent and the wave should have the same amplitude. We can also use a stroboscope to view this image, or we can also use the camera. That is how the pattern will look like at the base. The vibrations are there, the two dippers are vibrating, and you can see a pattern of the ripples. This is, as you can see, these are dippers are there moving to and fro, and as a result we see a pattern there at the bottom. And some places you can see they cancel out the effect of each other, like some places enhance, some places cancel out. May not be very clear, but some places they are canceling out the effect of each other. Here it's more prominent when it is closer, that a destructive and a constructive interference. So we can use like a stroboscope can be used. Stroboscope, it's like it's same concept. Like if I'm moving any object at a same speed and observing its frame in the same time interval, so I don't find there's a change in the position. So light from the lamp above the ripple tank is shine onto the water, through the water onto the screen below. One way of seeing this illuminated pattern more clearly, because this pattern is continuously moving. So if the like the wave is continuously moving, the wave move from this position to this position in 0.2 seconds. Then here also 0.2 second. And I use a stroboscope which is also capturing or flashing this after every 0.2 seconds. So what it appear? It appeared that object is being freeze. Like I don't see a change in the motion because I'm every time I'm looking at the image, the same image. That even though it is a moving, but every time we are looking at the same image, that's why it will appear as a freezed image. So using a stroboscope, we can just freeze this. The speed of a wave is 0.4 meter per second. Calculate the period of the wave. So we have the formula V is equals to F lambda. If we need the period or the time period, frequency is the reciprocal of the time period. So we can say V is equals to 1 over T into lambda. If I need T, T is equals to the time period is equals to wavelength divided by speed. So speed in the question is given 0.4 meters per second. What about the wavelength? In the question, they mentioned the wavelength of a wave 6 centimeter, which is 0.06 meters. So we'll just substitute the values 0.06 divided by 0.4. So 0.06 divided by 0.4, we got 0.15 meter, 0.15 seconds. That is the period, like in this 0.15 second, it will complete it one oscillation or one vibration. Next is figure 5.1 shows a point X that lies on a crest of a wave D1 and a midway between the two adjacent crests of a D2. This is a point X, like it is where it is lying. It is lying on the crest of D1 and it is lying in a midway of a D2, like the waves of a D2. If these reds are representing the waves of D2, and the blue is representing the waves of D1. What kind of interference will happen or occur here? Because at this position, from D1, it is a crest. But for D2, it will be at this point, there will be a crest of D1, due to D1, and there will be a trough of the D2. If the crest is joining with the trough, so what kind of interference they will have? Because of D1, it's a crest at point X. But because of D2, it is a trough. So if a crest is joining with a trough, what kind of interference they will have? They will have a destructive interference. Why destructive interference? Because crest is joining with the trough. If I mention a point, another point, let's say this point, point Y, what kind of interference will be there? There is a crest of D1, the red line, and there is a blue line also, the crest of the D2. So if the crest of one wave join with the crest of another, so the D1 crest is there and it combined with the D2 crest. So when they will combine, they will enhance the effect of each other. So we'll have a constructive interference. But if the crest of the one is combining with the trough of another, so as a result, the two waves will cancel out the effect of each other and we'll have a destructive interference. So for a constructive interference, what is the part difference? Minimum part difference, it should be 0 or lambda, or 2 lambda, 3 lambda. And what about the phase difference? It will be 0 or 360 for a constructive. But if it's a destructive interference, what should be the Part difference minimum, it should be lambda by 2, and the phase difference should be 180 or a pi radian. Because this is a fixed rule that whenever there's a destructive interference, they cancel out the effect of each other. And it's a constructive interference, they will enhance the effect of each other. So the question is, for wave at point X, state the path difference. So what will the path difference? One wavelength, because we identify it's a destructive interference. It should be 6 centimeter for a constructive, but for a destructive, it should be half of the wavelength, so it should be 3 centimeter. What about the phase difference? What about the phase difference? So in degrees, they ask here shows, so it will be 180 degrees. On a figure 5.1, draw one line at least 4 centimeter long with joins point where only maxima of the interference pattern is observed. So we want to draw a line which is 4 centimeter, at least like minimum 4 centimeter. First, we can just mark these position where the interference, like where we will have a constructive interference. This point will have a constructive. 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 And this point will also have a constructive. So what we do, we can draw a line here, minimum 4 centimeter. There's also another. This will be a constructive. 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 So I can join these points because I don't have, like my figure is not up to the scale. I have to draw at least 4. Maybe some of the lines might be less than 4 centimeter. That's why I may not include it. So we have to draw a line which is joining a point where only maximas are possible. And at least minimum 4 centimeter long. If this line is not 4 centimeter, we won't draw that. And not only in this way, there are multiple ways we can draw this line. Like you can have, this is 1, 2, 3, 4, 5. So maybe when I join, this will also be a constructive interference. What there's 1, 2, 3, 4, 5. 1, 2, 3, 4. So maximum I have 1, 2, 3, 4, 5 in this. So definitely this will be the longest line. Or I have 1, 2, 3, 4, 5 in this. So maximum, we just have to draw a line with the maximas are there on it. In question 5, a loudspeaker oscillate with a frequency f to produce a sound wave of a wavelength lambda, and a loudspeaker makes n oscillations in a time t. State an expression in terms of some or all of the symbols, the distance moved by the wavefront in time t. So how much distance these wavefronts will cover? These are the number of oscillations in time, like number of waves or number of vibrations are there. If I want to know the distance move, I can simply do what? I know the number of the wavelengths. So if total number of oscillation in time t, that is what we have. If total number of oscillation multiplied by one wavelength, I will get the total, like, see, this is 1, 2, 3, 4, and let's say 5. And I have one wavelength. I have one wavelength, which is example 2 meter, example. And I have 5 oscillations. I have 5 vibration. So how much distance is covered by the wave? So to know the distance covered by the wavelength multiplied by number of the waves. So 2 multiplied by 5, I can say that this wave has covered 10 meters. So distance moved, it's the number, the wavelength multiplied by number of the oscillation or number of waves. So I know the length of one wave, I'll multiply by the total number of waves. So I'll know that how many waves, how much distance the wave, these number oscillations will cover. Then we need for time that the total time it take to reach there. So how we can work out this expression for the time? If we know the number of, because this t time is not a time period. If it was a time period is a total time divided by number of oscillations. That is what is the time period stand for. We need this t. So if I need this t, it will be time period multiplied by number of oscillation will be equals to t. But we don't have time period, we have frequency. So, and time period and frequency are reciprocal. So instead of this t, I can write 1 over f. So n over f will be equals to t. Is it clear, this formula? How I got the time it takes to reach? Because we don't need the time period. We need the time it takes to reach from one position to another. For the first formula, if you want to use the first formula, if you need the distance, speed is distance divided by time. So distance will be speed multiplied by time. So speed is what? Speed is, the wave speed is frequency times the wavelength. So if you write f lambda t, that is also fine. And here you need the total time, as we need the total time. So we use a formula that V is equals to F lambda. We can use that as well. Or you can also use another formula, which is the time period is a total time divided by number of oscillation. And if I need the total time, so it will be a time period multiplied by number of oscillation. And reciprocal of a time period is frequency. So N over F is equals to T. That's why we put N over F here. Use your answer in A1, deduce the equation related to speed of a sound. So the equation which relate the frequency, use your deduce the equation that is relating the speed, frequency and a wavelength. So what is V is equals to F lambda is there. That is this is a general equation, equation of a motion, and it is valid for all kind of wave. Even it's a light wave, sound wave, it will work with all kind of waves. Then it's a CRO, a waveform of a sound is displayed on the screen of a CRO. The time base is 0.2 milliseconds per centimeter, means one box is equivalent to 0.2 milliseconds. Determine the frequency. So 1, 2, 3, 4 boxes are there. So 4 multiplied by 0.2 milliseconds, 10 to the power minus 3. So it will be equals to 0.8 into 10 to the power minus 3. That is the time period. If we need the frequency is a reciprocal of the time period. So it will be 1 over 0.8 into 10 to the power negative 3. So that will be about 1250, okay. 1250 hertz, that is the frequency of this wave. So this is a time base is a x-axis and the vertical also is there. Where did 4 come from? Because first what we did, we work out the time period. Time period means time to complete one vibration. This is one vibration. One vibration is in 4 boxes. One box stand for this, 0.2. Like time for one box to move in one box is 0.2. There are 4